Hi there everyone and welcome back to the channel. This video is the first in a multi-part series of videos I'm going to be doing on configuring and tuning the Ardupilot flight control software. This is going to be my biggest tuning guide ever because there are so many tips, tricks and tools that can help improve the flight performance of Ardupilot drones. In this video I'm going to be taking you through the first time setup of a brand new Ardupilot drone, getting it configured and ready for the first hover test. It's a lot to cover in one video, so let's not waste any more time. Let's dive right into it. Before we dive into the main part of the video, I just want to give you an idea of what I'm going to be covering in the rest of this tuning series. We're going to be looking at the tuning of the whole Ardupilot control stack, starting with tuning the filters, including the gyro and accelerometer low pass filtering, RPM and fast Fourier transform harmonic notch filtering, and the PID filters on error, derivative, and target. Then after that, we're going to be looking at PID tuning for the rate controller. So looking at the roll, pitch and yaw axes and getting the PIDs dialed in for a perfect rate tune. After that, we're going to move on to the stabilize or attitude tune and tune the roll, pitch and yaw axes for the angle controllers so that the drone holds angles in the air really well. Once the stabilize tune is done, we're going to be looking at some of the more advanced tuning aspects, like the altitude hold tune, looking at the vertical position, velocity and acceleration controllers, and the loiter tune, so looking at the tunes for the position controllers, velocity and acceleration as well. Once all that's done, we're going to be covering the parameters that control how the drone behaves in loiter mode and also waypoint navigation as well. It's a huge amount to cover. We're going to be taking it step by step and we're going to build up from the lowest level all the way to the highest level so that as you follow along with me, you're going to be able to get an Ardupilot drone tuned to perfection. This tuning guide on YouTube is targeted at hobbyists and members of the community who are looking to build, configure and tune their Ardupilot drone up to about an 8-inch prop size. If you're looking to build and tune something much larger than this, or you need a professional tune for more demanding commercial and industrial applications, then this is not the right guide for you. I'll put a link down in the video description to my Ardupilot tuning course that is specifically designed for professionals who are looking to tune much larger drones. And it also comes with one-on-one support from me to make sure that that tune is going to go smoothly and you're going to be able to get that drone dialed in perfectly and safely, even if you've never worked with Ardupilot before. Make sure to check out the link down in the video description if you're a professional and you're looking for an Ardupilot tuning course. Now let's dive into the main part of the video. Before we dive into the wiring and setup, I just want to take you through the hardware that I'm going to be using on my test drone for this tuning guide. And it's hardware that you're probably very familiar with if you've ever built and flown an FPV drone before, or you've done anything with hobby drones in general. We're going to be using the AOS UL8 frame. This is a lightweight general purpose 8-inch frame. It's perfect for acrobatic flying and autonomous navigation. We're using it with the Matek H7A3 flight controller, but you can use any flight controller with an Ardupilot target. We're using a standard 30x30 4-in-1 ESC. This is the iFlight Blitz E55. We're using an M10 GPS and compass module. And it's important when picking a GPS module for Ardupilot that you make sure that it also has an integrated compass because Ardupilot really does need a compass. We're using an Express LRS 2.4 GHz receiver and a DJI O3 unit for video. But you could use a different video system like DJI O4, walk snail, analog, anything you want really, that will work just fine. Now that we've got our hardware together, it's time to start wiring it up. And wiring from the flight controller to the ESC is very important. If you have not bought a stack, that is a flight controller and ESC that are designed to work together, then you must carefully check the pinouts of both your flight controller and ESC to make sure that they match up. Some combinations will apply reverse polarity to your flight controller and burn it out on first power up. I've had this happen. I know other people have had this happen. It's very upsetting. Let's, for example, look at the Matek flight controller, the H7A3, and the iFlight ESC. You can see that the pinouts here don't match at all. And if I was just to plug one plug into the other, I could apply full battery voltage onto my signal pins and burn out my flight controller right away. Fortunately, if the pinouts don't match, then you can repin the JST 1.0 plugs using a pair of tweezers. I'm going to show you how to do that now. So let's say we found ourselves in the situation where the power and ground pins on our flight controller pinout were reversed from the ESC. Well, what we can do is if you take a pair of really sharp tweezers, you can just very gently lift the plastic tab in the JST plug. Now you don't want to bend this back too far because you don't want to break it, but you just want to lift it a little bit. And then if you just lift it the right amount, you'll be able to pull the wire out of the plug. Just like that. And we can do the same for the pin next to it. And then we can just swap them round and put them back in the reverse order. So I'm going to put the black pin back in. So I'll do the red one first, that'll be easier. Once you've pushed the two wires in, just gently with a nail press those little plastic tabs back down. And what you've done is you've effectively repinned the plug, so now we have the red and black wires reversed. Wiring from the flight controller to the GPS is really quite simple. If you've bought a combined GPS and compass module, you'll have 6 wires to connect, and you'll want to connect SCL on the GPS to SCL on the flight controller, SDA to SDA, TX on the GPS needs to go to RX on the flight controller, and RX on the GPS needs to go to TX on the flight controller. So the UART pins are swapped around like that. And you also need to connect the ground and the 5-volt wires. I would suggest that if your flight controller has 5-volt pins, which will power up when you plug in a USB, then those are the ones that you should use to power the GPS and the receiver. We'll get to that in a second. It's just so much easier if the GPS powers up over USB and you don't need to plug a flight pack in. On the Maytech flight controller, those are marked 4v5 to indicate that they'll power up from the USB. Make sure to make a note of the number of the serial port that you've wired the GPS to. So in my case, it's going to be RX3TX3, so the serial port number is 3. Wiring up the receiver is even easier. All you need to do is pick a different serial port. So in this case, I'm going to be using RX2 and TX2. Wire up the receiver TX to the flight controller RX and the receiver RX to the flight controller TX. And then also wire up ground and 5-volt. And again, I would use a 5-volt pin that is going to power up when you plug in USB. So on the Maytech board, it's marked 4v5. Rather than a 5-volt pin which only powers up from battery voltage. It's just so much easier if all of your electronics is up and running when you plug in USB rather than needing to plug in a flight pack all the time. Again, make a note of the number of the serial port that you're using for the receiver, and in my case that's number 2. Wiring up the Air Unit is also pretty simple. Just pick another serial port. I'm using number 6 and wire up TX on the Air Unit to RX on the flight controller and RX on the Air Unit up to TX on the flight controller. And then for power, you can either use an onboard BEC if your flight controller has one. So I'm using the 9-volt BEC on my Maytech board for the O3 Air Unit. Or if your Air Unit supports a wide enough voltage range, you can run it directly off battery voltage. But do just double check that the maximum voltage of your battery is less than the maximum supported voltage for your Air Unit. Once you've done that, make a note of the serial port number for the Air Unit because we'll need that later. If you'd like access to my entire Ardupilot tuning guide for hobbyists in PDF format, and not just the content in this video, but the entire guide, then that PDF is available on my Patreon. And it's a perfect quick reference to have beside you while you're working through your tune, just to refer to so that you know what the parameters are called, where to change them, and how to adjust them to get everything dialed in. I'll put a link to that down in the video description. Just click through, sign up, and then you'll be able to download the entire guide in PDF format. If your flight controller has an Ardupilot target, but doesn't come with Ardupilot flashed onto it, perhaps it comes flashed with Betaflight or another flight controller firmware, then you're going to need to flash Ardupilot yourself. Fortunately, that's pretty easy to do, and I'm going to talk you through it. The first thing to do is to go to firmware.ardupilot.org, link in the video description, and scroll down to Copter for multicopters, and then you're going to want to look for the latest folder. Inside latest, just scroll down and find your target. So I know mine is the Maytech H7A3, so I'm going to click into there. And you can see that I have a few options. I want ArduCopter with bootloader. So you want to make sure you have the bootloader included with your firmware file, because that's going to allow you to update to future versions of Ardupilot without needing to reflash the whole lot. So make sure to pick the ArduCopter with bootloader hex file and download that to your computer. You're also going to want to download and install the STM32Cube programmer software if you don't already have it, because that's what we're going to be using to flash the ArduCopter with bootloader hex file onto your flight controller. Now you need to put your flight controller into bootloader mode, and this is really quite easy. Find the boot button on your flight controller, so mine is just here. Press the boot button down and then plug in the USB cable. Then you can release the boot button and the flight controller is in bootloader mode. Once the flight controller is in bootloader mode, head on into STM32Cube Programmer, go to this blue menu and select USB, and then hit this refresh button here to update the ports, and you should find a port USB 1 with the serial number of the STM32 micro that is connected on your flight controller. If all that's working, hit connect, and you should come up with a load of data here just showing you what's on the chip right now. Obviously we want to reflash the chip to Ardupilot, so we're going to go to the erasing and programming menu, and we're going to do a full chip erase. This is going to wipe everything that's on the flight controller right now and get it ready to take ArduCopter. So we're going to click this full chip erase button and it will give us a confirmation, and we just hit OK to wipe everything on the chip. Once everything has been wiped, you're going to want to select the new firmware path. So go and choose ArduCopter with bootloader that you just downloaded, select that. Make sure to tick verify programming and run after programming. And then you can also tick full chip erase, but I mean, we've already done that. Once that's all done, hit start programming, and that will reflash the chip with the Ardupilot firmware. Once that's complete, just unplug and replug the USB to power cycle the chip. To check that the firmware flash has worked, plug the flight controller back into your computer, open up MissonPlanner and go into the top right, set the port to auto and hit connect. With any luck, MissonPlanner will be able to connect to the Ardupilot firmware running on your flight controller, and you'll see Mavlink connecting followed by getting parameters. If you see this, then everything is working correctly and you can move on. There's a link down in the video description to where you can download MissonPlanner, but you should be aware that there is a bug with the latest version of MissonPlanner as of the time of this recording, which is 1.3.82. And that bug basically makes it impossible to download logs from the drone over USB. It's just incredibly slow. It's basically unusable. So for what we're going to be doing, we need to be able to download logs. So you're going to want to use either version 1.3.81, so the previous version, or you can apply the beta updates from the help page. If you go to the help page in MissonPlanner and then click check for beta updates, that will apply the updates, one of which fixes this logging bug. Now that everything is wired up, flashed and connected correctly, it's time to start the setup. And we're going to do that by going into the setup tab under mandatory hardware frame type and choosing our frame class. Now there are a whole bunch of different classes of frames that are supported by ArduCopter, mostly depending on how many motors you have. We've got a quadcopter, hexacopter, octocopter, a coaxial X8, a coaxial Y6, heli and Y3 configurations. We're going to be using the quadcopter class, and then you have a few different frame types depending on the layout of the motors. The plus type is if you have a motor directly in front of the drone. X is probably the most common, where we have two motors on either side. And the V-type is for drones which have slightly shorter front arms and longer rear arms, which is common for camera type drones. And that's what my drone is. The UL8 is a V-type drone, so I'm going to be selecting this one. Next, we're going to do the initial tune parameters. And here we're going to set the prop size in inches, the battery cell count. I'm using a 6S pack, so it's going to be 6 for me, and the fully charged cell voltage and fully discharged cell voltage. You can either set these manually, or you can just select the battery chemistry from this drop down and then it will populate them automatically. You're also going to want to tick the add suggested settings for 4.0 and up, which includes settings for battery failsafe and also sets fences, which is like an altitude limit and things like that. If you don't want to set battery failsafe and altitude limit, then just leave that box unticked and hit calculate initial parameters and then write those parameters onto the Ardupilot firmware. The next step is to set up your board orientation. Now, you'll only need to change this if you're using your board in an orientation that's different to the orientation that the manufacturer expects, the manufacturer default. If you need to change it, you can go into the Config tab in MissonPlanner, go into the full parameter list and search, the search box is on the right-hand side, search for AHRS_orientation. You should be able to find this parameter and then you can set it to the correct value based on how your board is orientated. For example, Matek expects that the H7A3 is going to be set up so that all of the components are facing downwards. Now, in my case, that would mean that all the components are right next to the ESC, and I'm worried about interference having all the components right next to the ESC. So I'm going to be flipping the board over. I'm going to be flipping the board 180 degrees on the roll axis. So I'm setting my board orientation to number 8, which is 180 degrees roll, and that's correct for me. If you're using your board in the standard orientation, then you don't need to make any changes, just leave it set to 0. But obviously, if you've got a different board orientation, this is where you set it up. Once the board orientation is set correctly, it's time to move on to calibrating the accelerometer. And to do that, we're going to go into the Setup tab, Mandatory Hardware, Accel Calibration, it's just here, and you can see we have 3 options. We're going to do the Calibrate Accelerometer first, then we're going to reboot the flight controller, and then finally we're going to do the Calibrate Level. To calibrate the accelerometer, you just need to follow the instructions on the screen. So you click Calibrate Accel and it will tell you to hold the drone level. Just hold the drone approximately level, keep it nice and still, and then click Done. Then you'll be told to put the drone on its left side. And again, when you've done that, hold the drone nice and steady and click Done. You'll then be asked to do the right side. Again, click Done. Then nose down, click Done. Nose up, click Done. And finally, hold the drone on its back, nice and level, and click Done. Once you've calibrated the accelerometer, then you're going to be calibrating the level of the drone. Here, you want to take the drone and put it on a nice flat bench like this. Leave it nice and still, step away from it, and then click Calibrate Level. That will set up the true level for the drone, and that's what's going to be used in the stabilize mode to keep everything nice and still. So it really does help to make sure that that level is really accurate. Once you've calibrated the accelerometer and calibrated the level, you don't need to do anything else. So typically you won't need to use the simple Accel Cal at all. That's for much larger drones that you simply can't do the normal calibration with. Once the accelerometer is calibrated, we can move on to the compass. And here we're going to just go down to the onboard mag calibration and hit start. Now the best way to do a compass calibration is actually very similar to the way we did the accelerometer calibration. And it also does help here to have a nice long USB cable. So to start with, we're going to take the drone and hold it level and then do a full 360-degree rotation, nice and slowly to the left. And then a full 360-degree rotation, nice and slowly to the right. Then we're going to put the drone on its left edge and do another 360-degree rotation to the left, nice and slow, and then back to the right again. Now put the drone on its right-hand side and do exactly the same thing. So rotate to the left and rotate back to the right. Now put the drone nose down and again rotate left 360 degrees and then right 360 degrees. You can probably see where this is going. Now we go nose up and again 360 degrees left I'll try not to drop the drone and then 360 degrees right. Now put the drone on its back 360 left and 360 right. The compass calibration should be complete after that process, and MissonPlanner will ask you to reboot the autopilot, so just power it off and then power it back on again. If for any reason the compass calibration hasn't completed, don't worry, just continue to do the process. Just start from the beginning and do all the rotations again, and that should, you might have to do it several times, but that should get the compass to calibrate successfully. If the compass won't calibrate no matter what you do, then it may be that it's too close to some big electrical wires, or it's too close to the motor magnets, something like that. Try repositioning the compass so it's nice and far away from any current carrying wires, like the battery leads or the motor wires, and it's nice and far away from anything magnetic, like the magnets in the motors. And then do the whole process again, and the compass calibration should complete. Once the compass is calibrated, it's time to check your radio channels. And for this, all you need to do is make sure that your receiver is bound to your transmitter. So for Express LRS, that's really easy. You just power the receiver on and off quickly 3 times in succession to put it in binding mode. Then it will double flash its LED to indicate it's in binding mode. And then you can bind it using the bind command in the Express LRS Lua script on your radio. So that's really simple. Other radios will have different procedures. Once you've got it all correctly bound, you should see an image like this, where all of the different channels are populated with green bars, and you want to check that the center stick positions are exactly 1500 and adjust the trims on your radio to make sure that's the case. The low stick position should be less than 1000, so in my case it's 988, and the high stick position should be more than 2000. In my case it's 2011. Now it's time to set up the servo outputs, and for a simple ArduCopter setup, your only servo outputs will be the motor outputs for your ESC. And you're going to want to set your servo outputs 1 to 4 to motor 1 to 4. Now, I need to make you aware that for typical 4-in-1 ESCs that don't follow the Ardupilot motor layout, so if you're using an ESC that's intended for Betaflight or something like that, the correct servo number and motor number won't match. They won't be the same. So servo 1 won't be motor 1, servo 2 won't be motor 2. They'll be in a different order. We're going to address this later on during motor test, so don't worry about that now. For now, just set servo 1 motor 1, servo 2 motor 2, servo 3 motor 3, servo 4 motor 4, and then we'll change the order around later when we look at motor test. Once you've set the servo outputs, it's time to configure the serial ports. And this is going to depend on how you've wired up your flight controller. So refer back to your earlier notes to remember what number serial port you connected each of the devices to. Serial port 1, UART1, is typically set to the Mavlink 2 protocol. Leave that alone, don't touch it. That's important for connecting to the flight controller over USB, so just leave that one alone. I connected my receiver to serial port 2, UART2, and so I'm going to set the protocol to RC in. And for the RC in protocol, the speed doesn't matter. It's going to auto detect the correct baud rate. So you can just leave that as it is, 57,600. For UART3, I connected my GPS to that. So I'm going to set the protocol to GPS, and I'm going to set the speed to 57,600. That's a typical speed for most GPSs. The Air Unit is connected to UART6. So I'm going to set the protocol to DisplayPort for most Air Units. And I'm going to set the speed to 115,200, which is the typical baud rate for that DisplayPort protocol with Air Units like the DJI 03 and 04 Air Units, the WalkSnare Air Units, stuff like that. Once the serial ports are configured, it's time to set up your ESC settings. And you can do that in the ESC Calibration tab. Don't click the Calibrate ESCs button. For me, this got my flight controller stuck in a loop where it just was trying to calibrate the ESCs every time it booted up. And it doesn't work for digital ESCs because they're not interested in being calibrated. So if you've got a digital ESC, a modern 4-in-1, and you're going to be using the D-Shot protocol, don't click the Calibrate ESCs button. You don't need to do it. You're going to want to set your ESC type to D-Shot 300. There's no point using D-Shot 600 with Ardupilot because the PID loop doesn't run fast enough to make use of D-Shot 600. So D-Shot 300 is absolutely fine. And you're going to want to set your output PWM minimum to 1000, maximum to 2000, and then the spin when armed, I would typically set that to somewhere between 5 and 10%. Probably start with maybe 5.5%, 6%, see how you go. The spin minimum, that can be 10%. So that's going to be the lowest throttle setting when the drone is actually flying. And then you're going to want to set the maximum spin to 1 because you're using a D-shot ESC, which means that there's no dead zone at the top of the throttle. You just want to set that to 1.0. Once your ESCs are configured, it's time to set up flight modes. And you can do this in the Flight Modes tab. You may find that when you start to configure this, that you would like the flight modes to be controlled by a different channel on your radio. You can accomplish this by going into the config tab, full parameter list, and searching for FLT mode_CH in the search bar on the right. That will help you find the flight mode setting, and you can change that to whatever channel on your radio you would like. I think by default it's channel 5, which is AUX 1, but you can set it to any channel. Once you've got the correct channel configured, you can set up the flight modes. I've got it set on a 3-position switch right now. So the top position is stabilize, the middle position is altitude hold, and the bottom position is loiter. But depending on what channel on your radio you're using for flight modes, you might want to set it up differently. This is where you do that. Once you've set up your flight modes, the last thing to do in the mandatory hardware list is to set up your failsafe. And in general, your failsafe should probably be RTL, so return to home and land. That means that if the drone loses connection or the battery voltage gets too low, it just flies back to where it took off from and lands there. And that's usually the safest. Defaults are pretty good, but it is worth just checking that the low battery voltage is appropriate. So 21.6 volts is totally appropriate for a standard LiPo, and that the low timer is right. So the low timer is how long the battery voltage needs to be below 21.6 before the failsafe is triggered. If you have your battery capacity set up correctly in Ardupilot, then you can also use reserved milliamp power to trigger return to land, your failsafe, when the battery only has that many milliamp hours remaining. But that involves making sure that you have your current sensor well calibrated and that you know your starting battery capacity. If you set it to 0, then that just disables the reserved milliamp power and it's just going to use the battery voltage. In terms of your radio, again, you should enable that failsafe, set it to always return to land, and then the failsafe PWM of 975 is absolutely fine. If you want to track battery capacity in terms of milliamp hours, here is where you can set the battery capacity. And you'll need to set that correctly and check that your current sense resistor, your current sensor is calibrated correctly if you want to use something like reserved milliamp hours for your failsafe, where you're actually tracking battery capacity in terms of milliamp hours rather than just voltage. Now that you've configured the battery monitor, it's time to move on to setting up the motor test. This is in optional hardware motor test, and before we do anything more, we're going to remove the props off the drone for safety. Now for a typical 4-in-1 ESC, your motor order is going to be wrong if you've just set servo output 1 equals motor 1, servo output 2 equals motor 2, etc. That's not going to be right. You must test and check that the correct motor spins and it spins in the right direction according to your diagram. You can find all the diagrams at this link here, which is linked in MissonPlanner, and I've also put the 2 common ones, Quad X and Quad V, up so that you can see them. Double check and triple check motor order and motor direction, or you may have a big crash on takeoff and damage your drone, and that will be heartbreaking. We don't want that to happen. If you're using a typical Betaflight 4-in-1 ESC in the usual orientation, then servo 1, motor 4, servo 2, motor 1, servo 3, motor 2, and servo 4, motor 3 should be correct, or at least a good starting point. But you will have to double check it yourself. The best way to do it is if you have servo 1, motor 1, servo 2, motor 2 set to begin with, test each motor. So test motor A, which will be motor number 1, and then write down like which motor that spins. Let's say it spins the front left motor. So you say servo output 1 equals front left motor. Servo output 2 equals back right motor. Servo output 3 equals front right. Servo output 4 equals back left. So you've got those written down. Then you can just set the motor number according to the diagram so that it's connected to the right servo, and then it should be fine. Writing it down on paper and just doing it systematically and methodically is the best way. Once you've got the diagram correct, and you've set everything up correctly in the servo output tab, which is in mandatory hardware servo output, you then need to check motor direction and make sure the motors are spinning the correct way according to your diagram. If they're not spinning the right way, any motor that's not spinning the right way, just tick the reverse checkbox for that servo output, and that will make the motor spin the other way. Sometimes this process can take a bit of trial and error, and it can be a bit painful the first time you do it, but just take it really slowly, carefully, write stuff down on paper, and it should go fine. And once you've done it once or twice, it'll get a lot easier and you'll get much more familiar with the process. Once you've got motor order and direction set correctly, you can look at compass interference. And this isn't essential to do, but it can be a good check. You need props on for this because you need representative amounts of current flowing through all the wires. So put the props on, but flip them over so the drone is pulling down onto the ground, and also secure it, strap it down in some way. Don't hold the drone with your foot or with your hand. Don't do it, it's not safe. Once you've got it all secured, hit start and then ramp the throttle slowly up to 50 to 75% for about 5 to 10 seconds and just check the effect on the compass reading. If the interference is less than 30%, then you're absolutely fine, carry on. If it's less than 60%, that might be okay, but consider relocating the compass. And if you're getting a reading over 60%, then definitely try and relocate the compass somewhere further away from battery wires, motor wires, or anything magnetic on the drone. Now that all of the hardware is configured, we can move on to looking at checking the settings ready for our first test hover. We're going to start by checking the gyro settings. Make sure that if you have an F7 or an H7 board, the INS fast sample setting is enabled and the INS gyro rate is set to 1, which is a 2 kHz rate. You can find these parameters in the MissonPlanner config tab full parameter list. And again, use the search on the right hand side to find the settings and set them correctly. These settings avoid aliasing of motor frequencies above 500 Hz, and this is really important, particularly for small quads where motor frequencies can often exceed 500 Hz, so you do want to set that fast sample equals 1. These settings should be set by default on modern boards, but it's worth checking. Now that you've set up the gyro settings, we can move on to configuring the logging, and getting the right logging settings is essential so that you have the information you need for later on in the tuning process. So you can set up the logging in MissonPlanner Setup tab, Optional Hardware, FFT Setup, and the sample count per batch, you're going to want to set that depending on what your INS gyro rate was set to. If it was set to 1 kHz, then you can leave it at 1024, that's absolutely fine. If your sample rate is 2 kHz, which is pretty much the standard for modern boards, then you might want to increase that sample count per batch up to 2048 to give you a little bit more frequency resolution. Ideally, we want to shoot for a frequency resolution of 1 Hz, and that's determined by taking the sample frequency and dividing it by the sample count per batch. So the higher the sample frequency, the larger the sample count per batch we need to get that 1 kHz frequency resolution. Typically, it's best to only log one of the IMUs. If you try and log more than one, the risk of logging dropouts and CPU overload becomes much, much higher. So I would just set that to IMU1 and leave the other two unlogged. In terms of the logging bit mask, I would enable everything here apart from mission commands, optical flow, camera, raw IMU. You need to disable raw IMU, otherwise FFT won't work, and disable video stabilization. All of the rest can be left on because we need the information from that to be able to do our tuning later on in the video series. The final logging setting which we need to configure is found in the MissonPlanner config tab full parameter list, and it's the INS log bat option. So just search INS log bat in the search bar and it should come up. You need to set that bit mask and tick sensor rate logging and sample pre and post filter. So have those both ticked. That will give you a value of 5 and write those parameters to the Ardupilot firmware, and your logging settings are now correctly configured. Now that you've got the drone correctly configured, it's time for the first hover test. And you want to do the hover test in the stabilized flight mode and in a wide open space so that if the drone does anything strange, it's not going to crash into anything. All you want to do is arm, take off, hover for a few seconds and then land. That's all we're doing. And then we're going to look at the log and start the tuning process proper. You may find when you're doing this test that the pitch axis is reversed compared to what you're used to with Betaflight, and that can be a bit surprising. I experienced that. If you do find the pitch axis is reversed, you can change that by setting the parameter rc2_reversed equals 1 in the full parameter list in the config tab in MissonPlanner, and that will fix that problem. Good luck with your first hover test. If you've made it this far, then your drone should be correctly configured and set up, ready to start tuning. And the next video is going to focus on the start of that tuning process, which is the filter tuning. We're going to be looking at tuning the gyro, low pass, and harmonic notch filters for the best possible flight performance. In the meantime, make sure to check out the links down in the video description so that you can get the entire tuning guide, not just this section, but the entire guide in PDF format on my Patreon. And if you're looking for a bit more support with a more challenging tune, maybe a larger drone or a professional application, then check out my Ardupilot tuning course, which is linked down in the video description as well. That's all I have for you for today. So until next time, I wish you all very, very happy flying.